So I think we're ready to go for the last talk of this session that is centered on data and data science. And this time we're going to focus on statistics and all the interesting ways that statistics can go wrong. Marco is the chair of PyData London, and he's going to tell us all about it. Give him a warm round of applause, please.
Thank you. Thank you for joining me today. Yes, I just want to tell you there are three types of lies. There are big lies, and there are statistics. So as a starting point, you can consider the following statement. In the Vatican City, there are 5.88 popes per square mile. And today I'm not going to lie to you. Okay, so the number is correct, plus and minus some rounding. But yeah, something fun is going on here, and that's the idea for the talk. Essentially, we are exposed to the use of statistics in everyday life, and we kind of assume that cold numbers don't lie, but that's not always the case. So statistics can be used to mislead people, to kind of bring different types of messages. And the assumption here is that you simply want to be a good citizen. You may or may not have some kind of a statistical background or some advanced degree in maths. You simply want to be a good person. So the first topic here is going to be correlation. When we talk about correlation, the clue is in the name already. Essentially, informally, we're talking about some kind of connection, some kind of relationship between two events or two variables or two things in general. But also formally, we want to measure the strength of this type of association. The simplest type of correlation that we can think of is linear correlation. For example, you have two variables. If they correlate, one goes up, the other one goes up as well, so that's a positive linear correlation. Or if one goes up and the other goes down, that's a negative correlation. As a classic example, let's talk about weather, a very British thing. So when the temperature goes up, the ice cream sales also goes up. And it kind of makes sense. There's nice weather, people go out more and just have some nice ice cream. So we can see that there is a clear connection between the two variables here. We can see some kind of causality. But in the general case, maybe you heard the expression, correlation does not imply causation. For example, there are two variables that correlate here. So ice cream sales and deaths by drowning. So there is a correlation. Now the question is ice cream really a killer? Well, there is a concept that we need to introduce, which is the idea of a lurking variable. So a lurking variable is a variable that is there, it's kind of looking at us, but we don't really see it. And again, talking about the weather, the variable here, the lurking variable, would be the temperature. So nice weather, people go out more and eat more ice cream, and similarly, nice weather means people go out swimming, and therefore there is more probability of people randomly dying by drowning. So the connection between the two variables, ice cream sales and deaths by drowning, happens through this lurking variable. Another example of lurking variable is in the case of fire accidents. And we notice when we observe fire accidents, if you deploy more firefighters, the damage is much bigger. So, policymakers, when they decide to cut budgets, maybe they didn't take a class in statistics. The question would be if we deploy less firefighters, maybe the damage would be smaller. Obviously, the case here is that we deploy more firefighters when the incident is bigger, and therefore also the damage can be bigger. Anyway, when we talk about correlation and causality, if you have two events or two variables, A and B, and they correlate, it's difficult to say beforehand what is going on. Essentially, there are many different ways of looking at things. Either one implies the other, or both of them together are the cause of a third variable C, or this third variable C is causing those two, or maybe there is some kind of transitive relationship, A to C and then to B, or maybe there is no relationship at all. So it's difficult to say beforehand. Just to give you some more examples of correlations. So over the years, the number of people who drown in a pool and the number of movies where we had Nicolas Cage appearing, they correlate. Also, the consumption of margarine and the number of murders by blunt objects. so marginally makes people aggressive. It's quite easy to blame Facebook for everything these days. Anyway, there is a correlation between the number of users on Facebook and the national debt in Greece. So more users of Facebook, more problems for Greece. The number of users of Internet Explorer and the number of murders in the US, they clearly correlate. And finally, one of my favorite, the consumption of chocolate per country and the number of Nobel Prizes per country. And you see the nice linear correlation. So more chocolate means more Nobel Prizes. There are a couple of outliers. There's Sweden having more Nobel Prizes than expected. Who knows why? And Germany, for once, not very efficient at converting chocolate into Nobel Prizes. So that was correlation. The next thing I want to mention is what happens when you have data and you start slicing and dicing your data. This is also called the Simpsons Paradox, which is a phenomenon observed by somebody whose name was not Simpson. As a textbook classic example, we have some numbers about university admissions, University of California in the 70s, and they reported some numbers labeled as men and women applications and the percentage of admissions. And there is a difference between the percentage of admission. So looking at the numbers, it's kind of fair to ask the question, is there any kind of gender bias going on here? Now, once you have this data, if you break things down and you look at the same type of information but per department, you see a slightly different story. So you see that for many, many departments, actually the percentage of women being admitted in the different schools is higher. And when you look at the raw numbers, basically what is going on is that men and women apply in bigger numbers for different departments. So you can see some departments where men apply with bigger numbers and others where it's kind of the other way around for women. So one way of looking at this could be maybe women apply for more competitive departments in general, and men tend to apply for the less competitive departments. So what is the story here? All the numbers are correct, so you can tell both truths, right? You can, well, tell the truth or lie in both directions. So that's what happens when you have data that you can group, aggregate in different ways, and when you have some kind of class imbalance, so the numbers are not equally spread. You can tell different stories. The next topic is sampling bias. So when we talk about sampling, essentially in statistics, we are focusing on some kind of subset of our population. So given a big data set, nowadays we live in the age of big data, so we have big data sets, and we cannot process, we cannot always process those big data sets. So focusing on a subset of individuals, the idea is that we can use those subsets to make some kind of estimate on the bigger population as a whole. So that's sampling. And when we talk about bias, in everyday language, there is a negative connotation for bias. So we talk about bias meaning prejudice or some kind of personal intuition, or there might be some cultural context to put in. But in science and in statistics, when we talk about bias, we are not giving any negative connotation. We're just saying there is some kind of systematic error. So sampling bias is some kind of error that we introduce when we are sampling data. And again, as a textbook example, there was a headline in a newspaper in the 40s, Dewey defeats Truman. So that's Truman, the day he became president of the United States, and he's waving a newspaper saying basically the opposite. He's smiling, of course. So what happened here is that the newspaper did a survey. So they had to go for print, overnight. They did a survey, and they trusted the result of the survey. The problem was that they did a phone survey. Now, in the 40s, people who had a phone at home, maybe they were not, representative of the broader global population in the US. So essentially, they were asking people who they voted for, but they were only asking a specific subset of the population, people who could afford at the time to have a phone. And that's what caused the survey to tell a completely different story and the newspaper to go out with a wrong headline. Related to sampling bias, there is another concept which is called survivorship bias. Survivorship bias is when we focus on the lottery winner and we forget about all the people who buy a ticket without winning the lottery. So often we see stories about leadership in technology and whatnot, and all the big names, they tend to be college dropouts for some reason. So Bill Gates, Steve Jobs, all those guys, they made a lot of money and they didn't finish university. So it's a fair question. Should we quit university? Should we quit studying? It works in both directions. So I didn't quit university and I didn't become a billionaire. Next, I want to tell you about data visualization. Data visualization is very important in the broader topic of data analytics because we can essentially convey complex messages using a simple picture. As one more textbook example, I want to showcase this data set, actually 4 data sets, where the summary statistics are all the same. So the average value for the variables, the linear correlation, the spread, and whatnot. But once you picture the 4 data sets, they tell a completely different story. So adding data visualization tells you something more compared to focusing on the raw statistics. And the idea is that we can use data visualization to convey complex messages. And often data visualization is used in storytelling as well. So, for example, there was some kind of a court decision in the US, and some newspaper decided to report the agreement between different politicians divided per political alignment. And it looks like, in this case, the Democrats were much more in agreement with the court compared to the other parties. For some reason, though, the axis starts from 50 rather than starting from 0. So when you show the real picture, yes, the Democrats are, agreeing with the court a bit more, but the story is a bit less loud, let's say. A different type of visualization and another kind of a hot topic for politics in the US, gun violence. A few years back, in 2005, in the state of Florida, they introduced a law that it's called the Stand Your Ground law. And they showcase that basically when they introduce the law, it looks like the graph of gun violence is going down. For some reason, though, the y-axis is kind of upside down. So reality is literally upside down. Okay. So they showcase the graph, but the y-axis was going down instead of going up. So when you flip the chart, that's on the right-hand side, that's the correct version. It shows a completely different story. One more example, this one is from one of the RAI channels, the Italian equivalent of the BBC. So the political editors at RAI at the time, they were in line with the government, so they did a survey, they're asking, is the government friends with the lobbies? And of course, being a friend of the lobbies is bad. They didn't like the results, so the 44% of people said yes, but then the slice became tiny, tiny slice. And I always thought, talking about politics and lies, back in Italy, we are a world champion at this until I moved to the UK. So something from the UK now, these are from a few years ago, so we're not talking about any recent event, so don't worry about it. So these are from 2 or 3 European elections ago, so many years ago, we already forgotten about those. And in the UK, the system first past the post essentially implies that the mainstream parties always suggest to avoid voting for the smaller parties. So these are lifted from the Tories, where they say, if you vote for the other party, basically, you're not going to win, you shouldn't waste your vote, you should stick to the mainstream parties. That's fine if that's your message, but for some reason, according to the graphic designer of the Tories, 42% is smaller than 32%. This is from the Lib Dems. According to the graphic designer of the Lib Dems, 12 is very, very close to 39. So if you normalize the chart, you can see there's a much bigger gap here. And then finally, on the labor side, again, same story, first past the post, so you don't want to waste your vote on the smaller part. It's going to be a race between two horses. And that's true. The problem here is that they forgot about the second big horse, so literally they removed the bar related to the Green Party here, which happened to be more or less on par with the Labour. So you can see, there's misdirections in all parties, essentially. One more topic, a bit more technical, statistical significance. Now, statistical significance is one of the most unfortunate terms, probably, because in everyday language, when we say something is significant, we kind of imply that it's also important. But that's not the case for statistical significance. So when we say results are statistically significant, we're not saying that they are important, we're not saying that they are big, we're not saying they're even useful for any kind of decision making. We're simply saying that we are a little bit more sure that the results are solid, right? That we don't see those results just by chance. So when journalists report on statistically significant results, often they kind of tell a different story. Now, related to the notion of statistical significance, we have a concept of p-values. P-values is one of those topics, when I was a student, basically, I couldn't understand what p-values were. And now, many years later, I wish I could tell you that I do understand now, but I'm still a bit fuzzy on that. So I tried to look it up, and it turns out I'm not the only one who is fuzzy about p-values. There is even a big Wikipedia page about what the p-values are not. So what are p-values? Well, p-values are about probability of observing our results, so probabilities, not certainty. And we're basically saying that we are a bit more sure about our results not being out of chance. Typically, when in a study scientists report statistical significance, they fix a particular level of significance, which could be 0.05, just arbitrary. Different fields will work differently, but we're simply saying, yes, we are a bit more sure that the results are not out by chance. Related to this notion of having a threshold of significance, there is also a malpractice which is called data dredging. That's dredging. Data dredging, also called data fishing or p-hacking, so we're trying to hack the p-values, happens whenever we try to brute force our data. Basically, the convention should be we have some kind of hypothesis, we collect the data, and then we prove the hypothesis or we disprove the hypothesis. Data dredging is what happens when you go the other way around. You get your data, you brute force the data, you find something that is statistically significant, and then you retrospectively come up with some hypothesis to match your findings. And that's something that is sometimes clear, quite visible in a paper, but sometimes it can be a little bit sneaky. So even experienced researchers might commit this kind of capital sin of doing p-hacking without realizing it. So we've been going a little bit up with the kind of level of technical details with statistical significance. Now a bit of bonus content. Twitter, social media in general, they're not necessarily nice places, and it's quite easy to find, opinions, especially from celebrities, all sorts of types, politicians as well, and they explicitly lie or they talk nonsense, but they would be kind of easy targets. Now I'm going to focus on instead Bill Gates. So Bill Gates, he's been doing a lot of work, in the past few years, in particularly fighting malaria with the Bill and Melinda Gates Foundation. And he's trying to make a point here about how the work they're doing is important, and he says, I'd rather encounter a shark in the wild than a mosquito. And he's reporting some numbers of that per year. That's fine, although where are the Bayesians in the room? Any Bayesian in the room? Well, he's basically flipping the causality here. So yes, of course, sharks will kill less people, but you also, I never encountered a shark in my life, but I have encountered many, many mosquitoes, so I still prefer to encounter a mosquito rather than a shark at the moment. So wrapping up, it looks like we are screwed. Everybody lies, and they can even back up their lies with numbers, so stuff out there. Well, what is the summary? The summary is that we should ask questions, essentially. Even if we have some kind of a mathematical background, some kind of statistical knowledge, we should not assume that we are immune. We should always ask questions. We should always ask whether the work that we're doing is formally correct, and what we read in the headlines, we should make a distinction between big headlines and actual good science. So the questions that we should ask are, what is the context, what am I not seeing, what is missing in the picture, who is paying for the particular study, and all in all, so what? We see statistically significant results, so what? So what is the implication? So adding extra context to what we read can help kind of understand better the world around us. So that's all for me. I think we have a couple of minutes for questions, or we can have a chat later about lying with statistics. Thank you very much.
Thank you. Right, we definitely have a bit of time for questions. So if you have a question, please raise your hand and I'll bring the microphone to you. Right, there we go.
Thank you very much for your talks. Very important comments there. I see a lot of these things very often. And another thing that I see quite often is people using means to describe distributions that are very skewed, that make no sense. So I would ask you if you have any reason to not use the median instead of the mean in some cases.
No, there is no reason. You should look at both. When you're doing your exploratory analysis, the mean will be skewed if you have outliers, and the median will be a bit more solid, a bit more robust, so it will tell you what to expect from the values. The only reason for reporting only one or the other is whether you have some kind of agenda. But for you, let's say as a data analyst or a data scientist, when you are looking into your data, you should look at both, because typically they tell a different story. Yeah.
All right, thank you. More questions? More questions down that road.
Especially in research, there is the problem of researchers that actually do be hacking sometimes on purpose. And I am aware that there is some initiative in order to reduce the chance of this, in order to basically do a pre-publication request and then basically state the content and the desire. But I don't know the status of this. Do you know anything about that? In terms of what is the decision in terms of scientific research? Thank you.
Yeah, I think it's an interesting question, and it's a difficult question. And the short answer is that I don't really have an answer, because there are pros and cons on both sides. So the whole push on preprint servers and uploading the research and also open reviews and whatnot, it all sounds like a nice idea in principle, but then again, this opens for politics and whatnot. Sometimes having your name there, if you're a student, you're not going to pick up on a big professor. So it's not so straightforward. In theory, yes, it would be nice if everything is kind of in the open. But the problem is academia, just like any other field, so research rather than academia per se, academic research is a place for politics at the end of the day. So there's no silver bullet there. Also, there was a push recently towards these preprint servers, which was a little bit too much in the sense that, yes, people started referencing papers that they were not really peer reviewed. They were in the open, but they didn't go through the whole peer review process. So that opens for further questions. So it's a bit of a you can't win, essentially. That's my take on it. And anyway, I'm happy I'm not an academic, so I don't have to publish. If I ever publish again, it will be because I want to do it, and I don't have any kind of a professional push to do it. But yeah, if you are in that kind of industry, yeah, it's not easy. And yeah, I don't have an answer, I'm afraid.
Hi, I actually took the microphone when someone asked the first question about pre-registered reports, but you've gone on to say that they point out some of the negatives in them. But I just say that one of the professors that's pushing for that is based in the psychology school in Cardiff, and he was one of my old tutors there. Mm-hmm. So I just wanted to mention that if anyone is interested. Oh, sorry.
Yeah, well, but I think in any case we're running out of time here. So once more, thank you very much, Marco.
All right, thank you.
For your talk. And I'm sure you can catch up